So, hello everyone. Welcome to our South American Geometry webinar. Let me ask Luis, can you please paste the instructions on the chat? So, before we move on, let me remind you that you can join our WhatsApp group for announcements and strictly announcements, as well as join our mailing list by sending the word webinar to the email provided in the chat. You can check our calendar of upcoming talks at the link provided, as well as previously recorded talks on our YouTube channel. We now have a new feature of a Google Agenda specific to our seminars, which you can add to your Google Calendar by clicking the short URL link below. Let me also announce, as a word from our sponsor, that we currently have postdoc positions being advertised under the Bridges collaboration in geometry, gauge theory, external metrics, and stability. One in algebraic geometry with Professor Marco Jardim, and another one to work with Lino Grama or Viviana Del Barco, all of us in UNICamp. So you can ask me later or some of the colleagues here for application instructions, but these positions are advertised on Math Jobs. Without further ado, let me introduce our colleague João Henrique Andrade from University of São Paulo. He's going to tell us about compactness of similar solutions to the GJMS equation. So João Henrique, thank you for being here. Let's do 50 minutes plus discussions, please.
Okay. Yeah. So thank you, Henrique, in the name of the organizing committee for the opportunity to speak here today. I chose to talk about compactness for solution to the GJMS equation because there's a very interesting connection between analysis and geometry in this problem. So I'll be talking about actually a series of joint works with my former PhD supervisor, Professor João Marcos Dubois, Professor Jess Ratsky from the Universidade of Würzburg, and Professor Jun Cheng Wei from the University of British Columbia. Okay, so that's the outline that I've been planning for this presentation. So I plan to introduce and to make some comments on the AMAP problem. Then I try to move on to some generalizations of this question. Then I'll set up what my objectives are. Then I'll try to discuss which are the ingredients on the proof of our main theorem. I'll be able to say what are the main results I'll be presenting in this talk. And I hope to be able to discuss some of the features in the proof and a little bit of some related research. Okay, so the AMAP problem is a classical, one of the most famous problem in geometry, in differential geometry, and it starts with a complete Riemannian manifold. So we're not making distinction to be either compact or non-compact at this moment. And we say that a metric is conformal if you can find a conformal factor such that you can write your metric like that. In this case, you denote like that the conformal class of your metric. So the AMAP problem is a kind of geometrization question and asks us whether you can always find a metric that is conformal to your background metric, and it has some interesting geometric feature that is having constant and scalar curvature. Okay, so let's now divide two cases to study the AMAP problem. So in the closed setting, I mean compact and without boundary, again with dimension bigger than 3, there's a standard computation of Yamabe himself, and it shows that to find a metric in the conformal class is equivalent to solve a semilinear critical PDE. So some terminology, again, you have a smooth metric on your manifold, And then this operator on the left-hand side is the conformal Laplacian. It appears naturally in the computations of Yamabe. And the point is, this operator has a zeroth order term, which comes in terms of the scalar curvature. And the problem is because of the conformal invariance of the equation, it turns out to be critical. And it's caused a lot of troubles to people in that time to solve the Yamabe problem. So the idea is this operator appears naturally when you try to compare the two scalar curvatures of any two conformal metrics. And turns out this problem was solved by some joint efforts of Yamabe, Trunzja, Aubin, and Shane. And it's very interesting because it was the first ever to be solved critical PD. And it developed a lot of techniques in the field to solve that problem. But it is even more interesting that at that point, people were trying to solve the Yamabe problem because you could see that as the first step to solve the Poincare conjecture, which turns out to have been solved in another way by Perelman. Okay, in the non-compact case, you can also ask about whether you can find a best conformal metric with constant scalar curvature. But in that case, it's not so simple. So you need to impose some structure at infinity of your manifold. Commonly, what you do is you take a k-ended asymptotically flat manifold, and then in this case, it makes sense to talk about what people call the developing map, which is defined by Shane and Yao. And then with this map, what happens is that no longer you have an equation on a non-compact manifold, but now you have an equation on a punctured sphere. And the number of punctures is exactly the number of ends you had generally for a manifold. So it's sometimes when you have non-compact Yamabe manifolds, what you do is you send your problem to a punctured sphere, and the structure of the singular set, which the number of punctures, depends on the structure of your manifold at infinity. Okay, so it's kind of right now, you have the same problem, but the background metric is the round metric on the sphere, but you have some singular behavior to happen near the singular set, which we're calling lambda. Okay, that's a picture of what we call k-ended asymptotic flat manifolds. And okay, what we're gonna do now is we're gonna put some structure on the space of metrics. So we're gonna furnish this space of metrics with the Gromov-Hausdorff distance, and then we're gonna define these two moduli spaces. Okay, we consider the moduli spaces of Yamabe matrix, only metrics with constant scalar curvature. And also in the singular case, in the non-compact case, we're gonna ask the metric to be also complete on the sphere minus the number of points. And I'm not saying here, but I'm quotientizing by the diffeorphan group of M to make this moduli space to be well defined. Okay,
in your definition, so in the compact case, we have a scalar curvature is equal to our n. What do you mean by
that? Yes, yeah, it's the scalar curvature of the round sphere.
Thanks.
It could be any constant. We just take this constant to normalize the problem, and it makes some computations to be easier. Okay, so there are some results about Yamabe metrics. They are very well known. Okay, so first, if you are in the setting with singularities, there's a classification of the local behavior given by conformally, and Spruck. One can also prove that this set of metrics, it's not empty. This is not so easy. It requires a gluing construction due to Museo and Packard. And when you are in the non-singular case, you know that if the manifold is not the round sphere, you have compactness. but there's a dimension restriction, and the restriction is between 3 and 24, and there are counterexamples for dimensions bigger than 25. Yes, this is this paper of Brandon and Marcus. And you can also ask whether you can put some structure on your space of map metrics. And turns out there's a famous paper of Mazzeo, Pollock, and Uhlenbeck that shows that this is in fact a Lagrangian k-dimension differential manifold, and the k is the number of singular points. Okay, so what we want to do in this talk is to extend some of these results to other type of curvatures. Okay, so in conformal geometry, you are always asking for some generalized curvature that also satisfies the same nice conformal properties of the scalar curvature. So there's this famous extension of Pennate and Branson who's extended this type of operator, this type of curvature for the fourth order setting. And just after that, the group of 4 people, Graham, Jean, Mason, and Sparling, they extend this construction of Pennate and Branson for any integer even order. And this is what we call the GJMS operators. And associated to these operators, you have the high order curvatures. So there's a very beautiful paper of Graham and Pfefferman, and shows that actually you can realize your manifold as the conformal boundary of a sphere, of a celestial sphere, in some Poincare-Eisen, so-called Poincare-Eisen manifold. So there's in this construction, you can see a direct relationship between general relativity and conformal geometry. Some people call this the ADS-CFT correspondence, or holographic duality. And okay, but at this point, there were only existence results for these operators. In 2011, you found extremely hard recursive formulas for these operators that I'm not going to show here because of the big content. So the idea is we have a manifold, and we want to construct a family of operators of any order M, and we're going to denote by that. And they have to be conformally invariant. And the main properties is that the leading order term is the Pauli Laplacian, and the zeroth order term is what we're going to call the Q-curvature. And we want this zeroth order term to satisfy this transformation law. So what I'm doing is I'm extending the notion of conformal Laplacian for any order, and that coincides with taking an operator whose leading order is the flat Pauli Laplacian, and the zeroth order is this function I'm defining, but there are a lot of low order terms, and they are very hard to compute. So if you have this operator, you can talk about what is the high order curvature associated to that operator, and it's just defining this on the constant equal 1. And in fact, what we're saying is that the curvature appears naturally as the zeroth order term of the operator itself. And that's the same thing that happens with the conformal Laplacian and the scalar curvature. But in the case of the conformal Laplacian, you don't have these low order terms because your problem is second order. Okay, so you can also extend these definitions for fractional settings, but then you need to make sense what your problem is. So you need to introduce the notion of no-smooth metric spaces. And again, these formulas are very hard to compute explicitly, but you can realize these formulas just studying some boundary reaction problem on a Poincare-Eisen manifold. And in some sense, what we want to have is an operator which is fractional, but the leading order is the usual fractional Laplacian, and you will have this zeroth order term, which is a curvature term we want to define. Okay, so in this talk, we're not gonna discuss the general case. What we're gonna do is, okay, in the round sphere, these operators have nice formulas. So this is the GJMS operator in the round sphere for n natural number, and it has like a nice decomposition structure in terms of conformal Laplacians, spherical conformal Laplacians. And in the fractional case, you also have this nice formula for what will be the fractional GJMS operator on the round sphere. Okay, so it's easy to see that if you have defined it for any number between 0 and 1 and any integer number, you can compose these two formulas and you define your operator for any sigma in this space. So you have now a continuous family of operators, and one of the representatives is the scalar curvature. It's the case sigma equals 1 in our notation. Okay, so with this notation, we can say what is this generalization of the AMAP problem. So we want to find again a conformal metric, and we want to have constant Q-curvature of that order, and we want to do that for any order. So it's a very general result, and it encodes all the results of Shane, Chunjia, Obani, Yao. And okay, so again, you have a analytic description of how you can find those metrics. So those metrics will be precisely given by solving the equation and taking this solution as a conformal factor. And again, you're gonna have a critical equation on your manifold, and the critical exponent is given by that, and this constant, it's again to normalize your problem and to have easier computations. Okay, you can also, so this is the case without singularities, so it's the compact case, but you can also pose the problem in a non-compact manifold. Now you remember that it's in a non-compact manifold, I can just send the problem to the punctured sphere by using the developing map of Shane and Yao, and I have this problem here, and now my operator on the left-hand side is this composition of the integer GJMS operator and the fractional one. Okay, so this is a very general problem that it's if sigma equals 1, so you have back your singular AMAP equation. So you can also, again, define the moduli spaces. So I want to prescribe this matrix on the conformal class to have this constant. And in the singular case, besides prescribing the metric, I also wanted the metric to be complete. And this is related to what we write here with this limit to blow up. It's equivalent to the metric to be complete. Okay, so again, this constant is not so important, but you can take that as the Q-curvature of the round metric to simplify your computations. So, okay, in the fourth order setting, there are some progress. So what happened is that the AMAP equation, the Q-curvature problem, is not solved, not fully solved. So you need to impose additional hypotheses in order to find a minimizer or a Q-curvature metric. So there are this first result of Gursky and Malchiodi, which was generalized by Heng and Yang under some hypothesis on the AMAP invariant. And also the compactness problem, it's even more interesting because you have results for low dimensions, which can be proven independently in two settings. But there are counterexamples for dimensions bigger than 25. Turns out it's open whether compactness hold in these intermediate dimensions. Okay, in the general case, when you have any order, there's a very recent preprint of Mazunda and Vetois where they prove the AMAB problem, they find a solution, but they need again to ask some condition on the AMAB invariant. And also, I'm not saying here, but it's encoded, you need some positivity assumption on the Green's function, because since you have a high order problem, it's not guaranteed that your minimizers will be positive, like just by definition. So you need some conditions on the Green's function of your operator. There's an even more recent paper of Case and Malchiodi where they ask the background manifold to be a specialized in product, and they're able to prove compactness results with some restrictions on the dimension again. And there's this paper of King and Raske that asks the manifold to be locally conformally flat, and then with some topological assumptions on the Poincare group of the representation by holonomy, you also have the existence, some existence properties of solutions for any fractional setting in this situation. Okay, so our now I'll say what's going to be the objectives of this talk. So I want to remember a classical result of Pollock for singular AMAB metrics. So the result is that if you take the space of singular metrics, complete metrics with constant scalar curvature, and you have more than 3 punctures, and you can control your what I'm going to define, which is the Pohojev invariant, then your solution space should be compact in the Gromov-Hausdorff topology, or sequentially compact in any C2 alpha Hilder space. And that's the reference for the paper of Pollock. So the idea is, again, what we want to do is we want to extend the results of Pollock for any integer order, any integer case. That's the main goal in this talk. So to be more formal, what we want to do is we want to consider this moduli space. So this is now, I have the moduli space of round metrics, and then I'm prescribing the M order curvature, and I have a singular set lambda of K punctures. So this space is sequentially compact, but I have to impose some conditions on how my sequence behave. So the statement would be that
Can I ask you something about this moduli space?
Yes.
Right. So normally, when we speak of moduli space, we mean satisfying a certain differential equation modulo some sort of symmetry.
Yes.
So is there a symmetry group, isometries? Is that quotient here telling me about?
Yes, I mentioned it's like I'm quotienting by the Diffie-Hellford group of the sphere.
Diffie?
Yes.
Okay.
Yes. Yes. So what I'm saying is that compactness is you can place compactness in terms of the metrics and the Gromov-Hausdorff topology, or you can place compactness in terms of the conformal factors. And the conformal factors solve a differential equation. So I'm gonna speak like openly. Sometimes I'm not gonna make a distinction when I'm talking about metrics or when I'm talking about conformal factors. But the compactness result is for both of these 3 structures. Okay, so these are my objectives. If anyone wants to, I think now it's a good moment to have if there's any questions on notation, because what I'm gonna do next is I'll present the techniques that I'm gonna use to approach this problem. Okay, so the first thing we have to do is you need to go into the punctures and you need to analyze what are the blow-up models, because that's how you prove compactness. You need to know what happens with your solutions near the isolated singularities. And this kind of techniques they come from the study of minimal surfaces by the very old theory of Lee and Simon on the asymptotic behavior near singular points for area minimizing currents or variables. Okay, so the idea is you can use the stereograph projection on the sphere, and you can send your problem to a near any isolated singularity. You just have to study a PDE on a punctured sphere, but now you are in the flat setting. You are in Rn with the round metric. And to do that, what you have to do is to take blow up. So you take the limit when your radius it's going to infinity, which is is not 1 over the radius is going. The radius is going to 0, but 1 over the scaling, 1 over it is going to infinity. So that's what you're doing. And what I'm saying here is that the flat polylaplacian is just like the penetrates the GJMS operator applied to the flat metric. And again, this problem is critical in the sense of Sobolev, and that's what causes most of the problems to study this type of equations. Okay, so the idea is to do what people call logarithm cylindrical change of variables, or Delaunay change of variables, Emmelin-Fowler change of variables. So what you do is you define a new function v using this formula. It turns out when you look at this transformation, what you're doing is you are using the conformal equivalence between the punctured space and the cylinder. So you're sending your problem to a cylinder. But in a cylinder, what happens, it's somehow magic that you have a simplification on your operator. So what you're gonna have, it's a ODE with constant coefficients. So you're gonna have just the operator. They are taken in terms of the higher derivatives of the t variable, but it's constant coefficient. So it's an autonomous operator. And the point is, once you have that, you can classify your blow-up limits. And now it's the first time there's a restriction on the number, on the order. So the classification result I'm showing now only holds for 3 cases until this date. So the classification is, if you don't have a singularity, your solutions, they should be bubbles, spherical bubbles, and they're given by this formula. If you have a singularity, solutions will be given by a conformal factor times a solution to an ODE. But this ODE, it's a very nice ODE. It has constant coefficients, and you can pose these initial conditions. So what I'm saying, all these constants you find, they are dimensional constants. So in the end, what you have is a constant coefficient high order ODE with some initial values. And then if you look at here, what I'm saying is that the solution is singular, but you know precisely how singular and how this solution behaves near the origin. Okay, so with this classification, we can say what is a spherical metric. So it's going to be the first case where you don't have a singularity, and these metrics they turn out to be not complete. The spherical metrics, they are not complete. The Delaunay metrics, though, they are defined by that, and they are complete. They are metrics that interpolate between the sphere and the cylinder. So this is the phase analysis, but this is the 2-dimensional one. What I can say is that in the high order cases, because of the structure of the coefficients, the same situation happens. So instead of having a higher dimensional or with more parameters, a solution with more parameters, you have only 2 parameters to parameterize your space of solutions, even if the order is bigger than 2, which is surprisingly in some sense. And these are the one-dimensional profiles. So in red, you see the non-singular solution, the bubble, and then you see like the cylindrical solution, which is in blue, and then the Fowler, these Delaunay solutions interpolate between the spherical and the cylindrical one. These are the after rotation, so they have one-dimensional they have radial symmetry. And this geometrically, what you're doing is deforming the cylinder until you get spheres, and then you would get like some non-embedded solutions to your problem. But what I'm saying is that the Delaunay solutions are this interpolation between the cylinder and a string of spheres. So once you classify the blow-up limit, you would like to study the local behavior. So the idea is you can show that solutions to your problem, to solutions near the isolated singularity, will behave like a type of eminent Fowler, a Delaunay solution. So what I'm saying is that near any end, solutions will be, and when I say and, I mean puncture, but you remember by the Cheyenne et al. Developing map, it's the same thing. When I say that a solution behaves like some blow-up limit model, I'm saying that near the end, solutions will behave like Delaunay solutions. They will be one of the solutions in this family, either a cylinder or this other type of more interesting ends. So that's how you should, that's how you should see the asymptotic result. You should see that for any metric you take on your moduli space, near a puncture, you will see a Delaunay solution. And so a Delaunay solution has a necksize, which is the minimal value at the origin. And so you can associate for any metric in any puncture a necksize. And that's a very important thing, because this is controlling the necksize will give us some conditions to have compactness on your moduli space. Okay, so another what I'm doing here is I'm setting the basis to say what are the main result and what are the techniques. So another very important feature and ingredient in the proof is what people call Pohojev invariance, and I'm going to discuss now. So I'm going to start with the simplest case. So if you have a cylindrical solution, so a solution to your ODE, you can define what is Hamiltonian energy. And it's just by integrating your equation. This is a feature of your problem being autonomous. So you're going to have this energy. And this energy, as you can see, goes increasingly harder as you increase the order. So here are like, you have some components, and your components will grow with the order of your equation. So the advantage of having a Hamiltonian is that you can integrate in Hamiltonian, since it's conserved. It's a conserved quantity. And when you integrate on the n slice of the sphere on the cylinder, you're going to have an invariant. And this is going to be called the Pohojev invariant. Okay, so what I'm going to do now is I'm going to use this invariant, and I know that near each puncture, I have a Delaunay solution. And I know how to compute the Pohojev invariant, the Hamiltonian of Delaunay solution. So I'm going to define what people call the radial Pohojev invariant. It's going to be, I'm going to look at the metric, and I'm going to look at the asymptotic expansion, and I'm going to compute the Hamiltonian of that expansion, and I'm going to integrate, and that's going to be my Pohojev invariant. So turns out that this invariant will detect singularities. If this invariant is 0, you don't have any singularity. If this is different of 0, you should see some singularity. So somehow this invariant is a flow around singular points. It detects this flow of the solution in this region. So as I mentioned, there are only expressions on the cylindrical setting. On the spherical setting, the formula is much more harder. So you would have like some function that depends on all the derivatives of your solutions. And it's not so easy to find this spherical Pohojev invariant, but the cylindrical one, it's fairly easy. But the interesting thing is you don't actually need the full formula, because the only thing that matters is the sign of the Pohojev invariant. So what you know is that they're going to have the same sign because you have this relationship between the radial Pohojev invariant for metrics, the cylindrical Pohojev invariant for solutions on the cylinder, and the spherical Pohojev invariant for solutions to original PDE. And they all have the same sign. Even a direct computation can show that, as I mentioned, if you always have Delaunay metrics to have negative Pohojev invariant and spherical metrics to have zero Pohojev invariant. I can say a little bit more about Pohojev invariance. What I'm going to say is that if you bound the Pohojev invariance away from zero, that's the same thing of bounding the necksizes. So the Pohojev invariant has the same monotonicity of the epsilon, the necksizes of Delaunay solutions. And that's the statement. That's what I'm saying because, and why I'm saying that, because in Pollack's first papers, the bound is on the radial Pohojev invariant. But then in our results, we're going to bound the necksizes because they are equivalent since we have that result. Okay, so I want to mention that the Pohojev invariant, it's a much more general homological invariant that arises in the theory of Gover and Oster, where they compute derivatives of curvature operators in a sense of nonlinear transformation. So the idea is you can look at the Pohojev invariant in the sphere as a function that takes a conformal Killing field and also a homological cycle. So the conformal Killing field is the field you're using to integrate your equation, often taken by del T. The homological cycle is the boundary of asymptotic spheres around singular points. So what I'm saying is that if you remember Shane's identity, it says that the Pohojev invariant is the derivative, in some sense, of the total scalar curvature functional. What I'm saying is that Gover and Oster they set a theory where you can compute derivatives of more general scalar curvature invariants that are not the scalar curvature. And I'm using this, I'm saying that once you do that, that's pretty much what you call the Pohojev invariant. And that's why the Pohojev invariant detects singularities. What is happening in our case, the cylindrical case, is that we're just taking a particular field, which is the radial field given by this operation here. But you can think about you could have taken other type of fields and get other type of invariants. Okay, so with this terminology, I already know what are the Delaunay metrics. I already know what are Pohojev invariants, and I already know what is the relationship between necksizes and Pohojev invariants. I can state my compactness result. So let us recall that we are considering this modular space. So we are taking conformal round metrics. We want this matrix to be complete, and this is the sphere minus the singular set. And we want to prescribe this high order curvature. So what I'm gonna prove is that you need to impose that your points, if you allow your points to move, which is not always the case, you need to impose that they should never be the same point. They should never collapse. And also the necksizes of your sequence of metrics or conformal factors, they should also be bounded away from zero. So that's what I'm saying with this modular space. Again, you're gonna put this Gromov-Hausdorff distance on these two modular spaces. And the theorem is the following. So it's here I'm allowing the order to be 2 or 3 or 4 or 6. if you prefer. And these are two different papers. One, we did this first case. The other one, we did the second case. And what we prove is that indeed, this set is Gromov-Hausdorff compact. Or we can even, this is like in the sense of Pollock, what we're saying is that if we don't have necksizes going to 0, because that would imply that the singularity is removable, and you have more than 3 points, and I'm going to explain why, then your space of metrics with this prescribed high order curvature is compact in this Gromov-Hausdorff topology. And these are the papers where the first paper in 2021 and the second paper very recently in 2024, where we proved these two results. Okay, so some remarks are you can change necksizes by Pohojev invariants, as in the statement of the paper of Pollock that I mentioned. And you can also allow your singular set to vary. Sometimes you're fixing the singular points, but most often you don't fix your singular point. You just say, okay, it's a set with cardinality equals k. And then you can also prove compactness in this setting. The classification result I showed, the one with the spherical metrics and Delaunay metrics, says that if k is equal 1, there's only the spherical solution. And so your moduli space is empty because the spherical solution is not complete. If k equals 2 and you have 2 punctures, then you are in Rn minus the origin using the stereograph projection. And then already you classified this solution. So your moduli space is an interval. Again, I'm quotientizing by the group, the diff group of the sphere here. And that's somehow what I'm doing here. And in this picture, I'm showing that if the necksizes go, some necksize go to 0, then you're gonna have some kind of degeneracy. So it's like in this case, your puncture is disappearing, in you liking the property of being compact. Okay, so I think I have a little bit of time to discuss the schedule of the proof and some of the ideas involved. So the first idea is you need to prove estimates, a priori estimates near your singular set. So the first estimate is an upper bound, and here I want to show where the order restriction appears, because in this case, if you want to prove that you have this upper bound singularity, upper bound estimate with precisely this power, you have to use, so the idea here is what people call blow-up analysis. So you suppose it is not true, and then you take a sequence, you rescale, and then this sequence will converge to a problem that you know the solution. And if you can classify the solutions, you can get a contradiction. But the problem is this classification is only true in this setting. So if you don't have classification of blow-ups, you cannot apply the so-called blow-up analysis of Lee and Simon. So the idea is once you have that, you can make a contradiction because you know that the boundary of any asymptotic sphere around singular points is mean convex. But this property, with this property, somehow you could show that it's mean concave, and then you would have a contradiction. So in this, to prove the upper bound, you strongly rely on the classification theorem for blow-ups. The other step is a lower bound estimate, and the lower bound estimate is where, so here you note that there are no restrictions on the order, because in this case there are only two things you have to do, is to analyze the sign of the so-called radial Pohojev invariant, and then you have to prove a removable singularity theorem classification. What is, if your metrics will have 0 Pohojev invariant, if and only if your metric has a removable singularity. And it's even more if your metric is the spherical metric. but spherical metrics are not complete. So that's the contradiction. That's why you cannot allow the Puncture invariants or the necksizes to go to 0. Otherwise, you'd have removable singularities. Okay, so the strategy of the proof is you take a sequence of metrics in your funny looking moduli space, but just remember you're prescribing the K order to 2M order curvature with lambda as a singular set, and you're not allowing the points to be distance less than delta 1, and you're not allowing the necksize to be less than delta 2. So it's a uniform bound on the distance between punctures and on the necksizes of metrics. So then if you have a sequence of metrics, you take the sequence of conformal factors that are associated to that metric. So by the upper bound, you can prove that this is the case, this is true. But then you can use this Ascoli theorem to extract a limit. The hard part of the proof is to show that this limit is not 0. To prove that, you need to use a Harnack inequality, and you need to use the assumption on the Puncture invariant. Because if that were 0, then your solution would be identically 0. So the other thing is you need to show that your solution is complete, your matrix complete. But this is equivalent to show that the limit of U blows up at a certain rate. And this is a consequence of the lower bound and the removable singularity theorem on the proof on this proposition, the last proposition I showed. So that's why this removable singularity theorem, it's a very important feature of the proof of compactness. Okay, so that concludes the proof of the main result. And in these final minutes, I'd like to talk about some related research that appeared when we were studying these problems. So first thing is, okay, I've taken a space of metrics and I proved compactness, but I've never mentioned if you have at least one metric. I didn't show existence of any metric in the modular space. So it's in this kind of, it's interesting that compactness paper, the compactness result, they came before existence result. But this is the case. So what I'm going to do now is I'm going to discuss when you can find conformal metrics with the properties we discussed, with prescribed high order Q-curvature and complete on outside the singular set. So we're going to define in two cases. We're going to have the degenerate case when you have non-trivial Jacobi fields, and that's where the sphere sits, because the sphere has this degenerate property. But we also going to discuss a little bit about the non-degenerate case when you don't have non-trivial Jacobi fields. So in both cases, if you want to prove existence, what you should do is you should use a gluing technique. You're going to take your blow-up models, which are the Delaunay solutions, the Delaunay metrics, and you want to glue them in to a central manifold with singularities. But to do that, you need to control the parameters in your Delaunay blow-ups. And this is done by a Lyapunov-Schmidt type reduction. So if you want to prove existence results, we should always have a gluing technique based on Lyapunov-Schmidt type reductions for the parameters in the blow-up models, which are the Delaunay metrics. I mean, the necksize in this case. Okay, so we will see that there's a huge difference between the degenerate case and the non-degenerate case. Okay, so the first question is, for any sigma, can we prove that you can find singular metrics with prescribed sigma order Q-curvature? And then in this case, I'm not even talking about integer. I'm allowing the sigma to be any positive, non-negative real number. And indeed, this was proved also And very recently, in a joint paper with EA and Wei, we proved that in fact you have a whole family of Delaunay metrics in this space. Another question we can ask is, what if you go away from the spherical setting? What if you allow your background manifold to be any metric, to be any manifold? Can we prove that this modular space is still not empty? And again, finding a metric in this modular space is equivalent to solving this elliptic equation with a singular set lambda. And the problem is, again, can we show that this modular space, it's non-trivial, is not empty? And the question is only partial, because we can only prove that if sigma is 1 or 2. So, and for not for any metric, we need to ask the metric to have a certain decay on the covariant derivatives of the Weyl tensor. And that's and in this case you can show that you still have the same family of Delaunay solutions, but no clue about whether you have compactness or not in this setting. So that's the paper where we prove for any sigma and the sphere the existence of these metrics, and that's the paper where we impose some conditions on the background metric, and then we can still construct the same family of solutions. So let me finish this up with some open and related questions on this problem. So it'd be interesting to prove compactness in the cases where we didn't prove. So any real number different for 1, 2, and 3. So this is all open. Also, this non-degenerate construction, it's also missing if you change the manifold not to be the round sphere. That's also highly desirable. And it also makes sense to allow your singular set to have higher dimensional singularities. Moreover, you can also define what people call a generalized conformally variational invariant that includes all the curvatures I mentioned, but also includes the sigma k curvatures and the renormalized volumes. And those 4 problems, they are widely open, and I think any contribution for this would be very nice. I think I'm gonna stop here. Thank you.
All right, let's take the figure. You can do it over the microphone or by clicking applause like crazy, like this. Yes, that's great. Are there any questions or comments? You can raise your hand by clicking the hand. If not, then I have a question. So, João, obviously you're talking about generalized curvatures, and you did mention the issue of homology in this context of Q-curvature. So, seeing as this community is particularly interested in that topic, perhaps you can maybe motivate Q-curvature from the perspective of Q-homology.
Yes, I think I think this is all about this ambient metric construction of Graham and Pfefferman. Okay, so there's 2 points actually. So I wanna discuss. The place where holonomy appears, it's when you have a non-compact manifold. And then when I was a PhD student, I started looking at these problems, and I asked, why people are taking singular problems, and they never mentioned that singular. It's because when you have this non-compact manifold, okay, here. So the point is, when you have a non-compact manifold, you can use this developing map. Again, you need to ask the manifold to be locally conformally flat, and this developing map goes to the sphere, and from the universal cover of M to the sphere. So the holonomy appears when you try to represent the Poincare group of this map. And when you look at the punctured sphere, you see what I mean?
Not quite. What's the holonomy around? It's what is the parallel transport?
Okay, it's because when you in this paper of Shen and Yao, they have what they call this conformally flat manifold and hyperbolic groups. It means that when you have this developing map that goes from the universal cover to the sphere, you can represent this quotient, the singular manifold, as a quotient, where this quotient takes a subgroup of the isomeries of the hyperbolic space. It's a kind of Klein model. You can always represent this universal cover as your manifold will be the universal cover quotientized by some element of this isomeric group, and this holonomy is the representation of this group of isomers. You see what I mean?
Yeah.
Yeah, but it's okay. It's just a very fast explanation of this general theory of Shen and Yao of developing maps. It's a much general. I mean, in this presentation, I've only taken lambda to be finite, but you can allow this singular set to be any very strange setting, like house with Hausdorff dimension bounded in some sense. So yes.
Then the other question I had is, obviously we've been discussing these moduli spaces, right? And but what in terms of their structure, it's not apparent to me why, for instance, they should be finite dimensional, even if you quotient by diffeomorphisms.
Oh yeah, I think this is one of the interesting results I like very much. Is this result of Erlenbach? Let me show you here. They prove actually that this manifold is k-dimensional if you have only isolated singularities, k. But if you allow, as I mentioned, the singular set to be not finite, then this manifold, this moduli space, is infinite dimensional. So there's it's even more. It's a Lagrangian. It has a very nice structure. This space of metrics.
It's very endowing the space of metrics with a symplectic structure, and then
yes. And the symplectic structure comes from the Pohojev, the Hamiltonians that I defined it along the way.
I see.
Yes. But the interesting thing is that there are no parametrizations of this, because what people have is that to prove that, there's a thing that I didn't say, but there's something called balancing laws for the Pohojev invariant. And these balancing laws, they are expected to be the equations of your moduli space, but they are not sufficient. Somehow there are some variables they are not encoded by the balancing law. So you know that it's finite dimensional, but you're not able to present like the parameterization you have. But the Pohojev invariant is like what you should look at as to be the defining guy of this modular space.
And does it still have a sort of Fredholm local model?
Yes. That's how you prove all the linear structure around the London metrics. You need to prove like Fredholmness properties for the linearized operator, and that's where you use balancing, because balancing kills the kernel of the linearization.
I see.
That's the.
And we don't know beforehand. Do we know that it's formally elliptic? The sort of definition theory is elliptic.
Yes, it's self-adjoint. It's self-adjoint.
I see. Okay.
Yes, all these high order operators, they are elliptic and self-adjoint. But the fractional cases, they are only pseudo-elliptic, but they have very nice symbols that you can analyze. And that's yes.
Cool.
Yes.
Have you got any more questions for Jean-Henrique? Well, if not, then let's thank the speaker again. You can clap or click like hell at the clapping button, which I find more elegant. Let's do that. You can click the other ones too. You can click hearts and OK.